Okay, let's see. Welcome once again to the GSM lecture series. Tonight we have another great lecture on the way. Before we get going, well, a couple of announcements ahead of time, then followed with the lecture, and then there will be questions and answers, of course, afterwards. Special thanks to Randy Strobel as the host. He and Dave Wilhelm and I are moderators. As always, thanks again for Randy for setting up the Zoom webinars, sorry. And special thanks to Steve Erickson for arranging another outstanding slate of topics and presenters. As with all of our live lectures, this lecture is free and open to the public, not just GSM members. If you are not a GSM member, please open the chat box and type in non-member and your city, state, province, country, whatever, or planet, doesn't matter. Also mention how you found out about us and how many people there are watching on your device. We could count the number of devices, but we cannot count the number of individuals watching. Okay. 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 For those of you that can use continuing edit credits for this, just put that into the chat that you need a form. Give us your email address and we will get one sent out to you. All right. Tonight, we have Sheila Alfsen. She's going to be talking about Mount St. Helens. And here's a couple of things that she's really into: paleontology from the University of Oregon, volcanology, oceanography, kind of covers a whole lot of things. Masters of Arts in Teaching from Western Oregon University. And I'm just reading some of the highlights here. 35 years in education, and an interpreter for the National Parks Service. She is an instructor at Portland State University. Researcher, just all around, very involved in geology in that area. And she also is the president of the Geologic Society of Oregon County in Portland. So let's give a warm welcome for Sheila. Thank you.
Thank you, Roger. I appreciate that. Actually, I'm not the current president anymore, so I sent you information that was a couple years outdated. But I still am the program director for the Geologic Society, and I've been involved with them. Mostly, I just love geology, which is, I think, why you were all here. So I'm very pleased to be able to present to you tonight. So let's get started, and I'm going to talk about Mount St. Helens. Mount St. Helens was the worst volcanic disaster in recorded U.S. history, not the largest disaster that we've ever had or the largest eruption we've ever had, but certainly the one that was the worst one since we've been recording. So what we're going to do in this lecture is we'll learn about stratocone volcanoes, the type of volcano that it is, and we'll examine all those events leading up to the 1980 eruption. Then we're going to see that big one and all its effects. And then we're going to look at some activity since 1980 and speculate about the future. So let's get started here. Before 1980, Mount St. Helens was called Mount Fujiyama of the US. Mount Fuji in Japan is the perfect cone-shaped stratocone volcano, and so is Mount St. Helens. And so it had the perfect symmetry and shape of a stratocone volcano. And that tells us now that we know about them that it's a very young volcano and erupting quite frequently. Okay, so Mount St. Helens was also had Spirit Lake in the foreground, and Spirit Lake was America's playground. Just Boy Scout camps, cabins everywhere, just the place to go for outdoor recreation in the summer. So what we're going to do in this lecture is we're going to recount the events that took place to change something idyllic, beautiful like this into this in a matter of minutes. So let's get started. These kind of volcanoes are called stratocone volcanoes, or sometimes called composite cone, but what they're made of is layers of volcanic material from repeated eruptions. So you have an eruption of material, loose material that falls in a pile around the vent, and then lava comes over and kind of caps it all off. And then this action repeats itself over and over until you build up this cone. So it's made of layers of repeated eruptions. The material comes from below the surface in a magma chamber. So there's lava. We don't call it lava at this point. We call it magma. It's only lava once it erupts. But, you know, and then we change the name of it and call it lava. But this material is forming in a chamber below the surface. And what it's coming from ultimately is the fact that we are on a convergent plate boundary. We have an oceanic crust off Oregon's coast that is diving under the North American continent, and it is creating melting that is occurring. There's chemical reactions and heat and release of pressure that initiates melting, and this molten material, this molten magma, is less dense than the surrounding rock, and so it starts rising to the surface. It'll collect in a chamber below the surface, and there it is until, if and when it makes its way to the surface, you have an eruption. So the magma chambers for Mount St. Helens are being fed by the subduction of what we call the Juan de Fuca plate, which is a small tectonic plate that is diving under North America and creating all the features in the Pacific Northwest. So there's a whole chain of volcanoes starting from Northern California, going all the way through Oregon, Washington, and up into British Columbia. This is exactly the extent of the margin of the Juan de Fuca plate, and that's where the volcanoes are. So our current Cascade Range that we know of, it started actually about 40 million years ago, but they've been eroding down, and the visible peaks are the new material, the newest manifestations, and they are all named with different names here, and they are built on layers of older volcanoes. If we look at this picture that I took, this is just adjacent to the current Mount St. Helens when I did my field camp there. And this is a ridge that was blown away bare by the eruption of Mount St. Helens, and you can see the layers here. This is the material that the high peaks of the Cascades are built upon. So if we look at all of the Cascades, and this is courtesy of the USGS, United States Geologic Survey, they've definitely, they can figure out which, well, it's not hard to look at this diagram and see who's been the most active during the last 4,000 years, which volcano, and by far it's Mount St. Helens. During the past 4,000 years, this has had more eruptions than any of the others. Okay, so in order to predict a volcanic eruption is critical with people living so close to volcanoes. So we look for certain things like bulges on the flanks of the volcano, dramatically increased heat flow. We start measuring as that magma is moving up, it's warming things up, and that can be detected, as well as changes in the local gravity, because the gravity of molten magma is less than it is of solid rock. So all of these give us clues. Of course, there's gas and steam eruptions, and even sulfur, you can smell it in the air, and that's also a precursor. But probably the best way to predict volcanic eruptions is with seismic activity, meaning small earthquakes, and a special kind of earthquake called a harmonic tremor. Now, this was first discovered after Mount St. Helens, done by research up in Alaska. This is Mount Redoubt up in Alaska. It was the first one to be predicted in 1989 using long period seismicity. This harmonic tremor is when it's coming, we know that the eruption is close. So we know that it's actually minutes away. So this method was used to predict an eruption of Mount Redoubt 30 minutes before the eruption. That's really getting down there to specifics. Otherwise, the thing is just having earthquakes, and people say, well, it's going to erupt, but I don't know if it's going to be next week or next month, but this gets it down there pretty specific. So in 1980, we didn't understand that very well. So we were on edge knowing that something was going to happen. And it caused several volcanic disasters. So we're going to kind of look at these events leading up to the eruption and what helped us understand, you know, the eruption itself. So in March of 1980, remember the eruption happened in May of 1980, May 18th. But in March, a couple months earlier, they started having earthquakes in the area, just small earthquakes, about a 2.5, because the magma was moving north, you know, moving up in the crust. If it finds its way to the surface, you have an eruption, but it's sitting there and it's building pressure. And it's cracking rock as it's moving upward, and this can be felt by seismic signals. So in early May, they started noticing something interesting. They started noticing on the north side of the volcano a bulge developing, and the summit of the volcano sunk down a little as the bulge pushed out towards the north. Okay, and so basically what it did is, it's lodging itself in here, building pressure, and but creating an oversteepened slope. And as anybody knows, if you make the slope too steep, you make it unstable and able to collapse. So what happened is on May 18th, early of the morning of May 18th, they had a larger than predicted larger earthquake, a 5.1, which is quite a bit larger than the earthquakes that they've been having. And that caused the north slope to fail. And so this became the largest landslide that we have ever witnessed in recorded history. So what it did is it rumbled down the whole north slope of the mountain, rumbled down the mountain, and that initiated, that was like taking the cork off the bottle. So this was, magma was in here building up pressure, and as soon as you release the top of it, it erupted. And it erupted in two different ways. You expect eruptions to go straight up, but this one did something interesting. It shot straight out the side. So we'll call that a lateral blast. We'll just refer to it that way. Now, this is interesting because we didn't know about them. A smaller one had occurred, though. With looking back in the history and reading the rocks around the volcano, we were able to determine that it had occurred earlier in the volcano's history. But in 1980, it was really basically unheard of. It was only after the fact that we went looking for it. And the extent of the area that was affected was completely unexpected. We expected it to go straight up, and instead it shot out the side. So I'll show you pictures of the damaged area in a minute here. But after the eruption, after the top blew off and it blew out the side, then enough of it was gone to establish the typical vertical eruption like you expect. So this is a picture taken the day before the eruption from an observation tower called Coldwater 2. And today we've renamed it as Johnston Ridge, named for David Johnston, the volcanologist who lost his life in the blast. He was the only one at that night manning the Coldwater 2 tower. But he actually realized it, but most volcanologists did not realize that he was looking down the barrel of a gun. He had an indication that these pyroclastic flows could come out and go not only down into a valley, but up over the ridge. And he knew the danger he was in, but he was willing to take the risk for the team. So let's take a look at, let's observe the sequence of events and photographs here. So I'm going to show you the bulge developing, and then I'm going to show you the landslide being initiated, and then the vertical eruption and the lateral blast being initiated. Lateral blast will take over the landslide. So the landslide happens, but then the lateral blast is moving much faster and it overtakes it, and then it completely overtakes the landslide. So I'm going to show you this series of pictures that was taken by Gary Rosenquist, who was just a photographer that was there on the scene hoping to catch the eruption. And these are now famous pictures of Gary's. So let's take a look at this. The morning of the eruption, early in the morning, sun is hitting it, and you can see the bulge here on the north side. I've kind of got the arrow down the wrong place. Bulge is right here. And you can see the top of the mountain has already sunk down. Okay, and then the mountain goes fuzzy. People that were observing it said, what's going on? But the mountain looks fuzzy. Well, it looks fuzzy because the landslide was initiated. The whole north slope of the mountain fails and moves down into the valley. And that just looks like a rippling effect. But that's taking the cork off the bottle. So here we've got a little bit of a vertical blast being initiated and that lateral blast. Lateral blast shoots out the side, and these pictures are taken seconds apart. So a few seconds later, it looks like that. And it's overtaking the landslide, and then it completely overtaking it. And so these were just seconds apart. About a half hour later or so, the vertical eruption initiates, and then that goes up 12 miles into the air. That's how we measure how big an eruption is by how far in the air it goes and how much ash it puts out. But when it shoots out the side, it's doing something that most people were not expecting at that time. In all, the mountain lost 401 meters or 1,200 feet from the summit, completely changed the look of it. So you can see where the old summit is. Now there's a huge steaming crater in here, and the whole top of the mountain is gone. Okay, this is a picture taken by, I did this talk several years ago, and a person named Charles Hall was there with his son, just hoping to catch, like many people in Washington were, driving around the mountain, hoping to catch the eruption. So they knew something was going to happen soon, but they didn't know how soon. And he happened to catch this. He was in a relatively safe place because he was south of the mountain. But you can see the magnitude of this eruption is huge, and most of it is going away from the camera, thankfully. So Charles and his son lived to record this in picture and gave it to me to share, which I'm always proud to share of. He said after that, his son was about 12 years old and became a geologist after this experience, which you can see why. So if you were impressed with the size of that volcano, as you should have been, let's look at how it compares to some other eruptions though. So Mount Vesuvius that buried the Pompeii was this size, and Mount Tambora in the Philippines, 1815, caused the year without a summer, put up this much material. And our eruption that we just saw on the compared to Krakatoa and even Mount Pinatubo was tiny compared to what a volcano can do. But I was pretty impressed with those pictures, as I'm sure you were too. Now, if we want to go even further, let's look at what Yellowstone would look like on the grand scheme of things. So this is one to watch. Okay, this is off the charts, the eruption of Yellowstone. So, and again, how we measure this, we have a VEI, volcanic explosivity index, which is like the magnitude scale for earthquakes. It tells you how big it is. And it's measured by how far and high in the atmosphere this material goes, and then how much ash it produces. And so this was the Mount Pinatubo eruption, which was about 3 times larger than the Mount St. Helens eruption. And you can't even see the volcano here in this picture, but I took that for just so you could see what other volcanoes look like. So let's look at the effects, though, of that May 18th eruption, and I'll show you, illustrate it with some examples from other volcanoes. So it caused the largest landslide that in recorded history, and that landslide is referred to as a debris avalanche. It caused a lateral blast in 3 different zones, which I'll outline for you. And then pyroclastic flows, which are gas-charged heat, ash eruptions that just take over the area. And then we had ashfall, of course. So enough went into the sky that was falling down. And then we had lahars. And this is when the snow melts and mix with that ash, and that comes down rivers as really powerful floods. So let's take a look at this map here, and you can see Mount St. Helens here, and the USGS put this together so you could see the area that was devastated by it. And notice the scale down here. So this distance here represents 5 miles from the volcano. So the pyroclastic flow, which is a very deadly flow of hot ash and gas, only reached about 5 miles from the volcano. And the landslide actually went all the way into Spirit Lake, but the landslide also progressed down the North Fork of the Toutle River about 11 miles away from the summit. And then, of course, this whole area in yellow was affected by the lateral blast, and I'll show you pictures of what it looked like. But the volcanic hazard that travels the farthest from the volcanoes are lahars, because they take over rivers and they flow. This one flowed all the way down into the, let's see, the Toutle River goes into the Cowlitz River, which then went into the Columbia, blocked shipping in the Columbia River. So this is definitely the hazard that reaches the farthest away from the volcano. So let's look at these. First of all, the debris avalanche creates hummocks or hills that you can see. So this is taken in the hummocky plain, just below the what's left of Mount St. Helens. The mountain would be right here in the background. But this is called the pumice plain, and you can see that it's just there's 200 feet of material. The floor of the valley floor was filled in about 200 feet, and there's all these hummocks in it. Boulders are strewn around the landscape. Some of these boulders were ejected out of the volcano, and they advanced down. They filled the Toutle River to 150 feet higher. Spirit Lake was filled about to 200 feet. After seeing those hummocks, we always wondered what these hummocks that are just north of Mount Shasta in Northern California, what they were. Geologists always wondered what they were, but the eruption of Mount St. Helens solved the mystery. And here's Mount Shasta in the background, and we're looking 25 miles away to the north, and you can see that this whole plain is littered with these little hummocky shapes. Now let's look at the blast zone, and let's divide the blast zone into 3 zones. Okay, so the peak of the volcano, or the edifice itself, the mountain itself, is right here. And then this area in dark orange is the direct blast zone. And then out on the outer fringes away from it is the channelized blast zone. And then finally, the very outer edges is the seared zone. And what we're referring to is the forest. Okay, this was all Weyerhaeuser forest land. This was, millions of yards of timber that was destroyed in this eruption. So let's look at it. The direct blast zone, nothing was standing. It looked like a complete moonscape. And what was left of these were full-size fir trees that were just sheared off. They were pulverized, incorporated into this furious cloud of pyroclastic ash and gas. And there was nothing left of it, nothing left of these trees at all. And in fact, people flying in a helicopter over it said they knew the landscape well previously. It looked like nothing they had ever seen before. It looked like they were on a totally foreign planet. In the channelized blast zone was on the outer fringes, and so the trees were blown down. And notice that you can see that these trees were blown down and they're all facing downwind from the blast. The blast just knocked a whole forest over. Now, when you look at this picture, you might be tempted to think that that is grass or something there, but these are full-size fir trees, Doug fir trees. So here, just to give you an idea of what it looked like, here's the workers. Here's the people there standing in that debris of channelized timber. And log trucks were no match for the lateral blast. Log trucks were thrown on their side and looked like Tonka toys. Okay, then finally in the seared zone, the trees were left standing, but they were seared. They were dead. And I took this picture about 25 years later, and you can see new growth. All this new growth has grown up since 1980. So, but this is a picture of the seared zone with all the trees missing. And then the interface between the seared zone and the untouched forest right back here. So you can see all these trees in the foreground are dead, standing, behind it, untouched forest. Guess where Gary Rosenquist took his pictures? Right here right at that interface. He was right on the edge. And luckily he survived and his camera survived. So he right here, you can see the seared zone and behind it, living trees. So he was right on the very edge. Did it cause a tsunami? Now we use the word tsunami to mean a seismic sea wave, but we'll use it in a loose term here, saying, what did it do to Spirit Lake? Spirit Lake was this gigantic lake north of Mount St. Helens. And what happened is the landslide dumped into the lake and splashed the water up on the shores. So let's look at a close-up of this point, and you can see here, if I zoom in, that you can see the trees here, the little white stripes here. That's what's left of the trees. There are no tree trunks, or these are the trees that were blown down in the blast zone. And below 200 feet, below that from the surface of the lake to an elevation of 200 feet above the lake, there was no trees. They're all here in the water. They're sitting there in the water. What happened is, and here's a close-up of it so you can see that peninsula, and you can see here the stripes, little stripes of the trees, and this level is about 200 feet. So what happened is now remember what happened is the trees were blown down first, but they were already, they were already there when the landslide came. The landslide happened first, landslide happened first, and then the blast. But by the time it got to Spirit Lake, the landslide is moving only about a third as fast as the pyroclastic flow or the blast. The blast is moving about 600 miles an hour. And so it reaches, even though the landslide is rumbling down the hill, the blast reaches these slopes, blows down the trees, and then the landslide plops into the lake, raises the level of the lake 200 feet, splashes the water another 200 feet. And so all of those trunks get washed down and they're all just still floating here in the lake. Okay, so let's look at these pyroclastic flows and let's talk about them for just a minute. Mount Unzen in Japan was having pyroclastic flows about 11 years later, and they were recorded. So you can see a little village down here in the foreground. You can see that these are ground hugging explosions of hot ash and gas. You cannot outrun them. This is a picture taken of a camper and the pyroclastic on Mount St. Helens, and the camera was recovered. In fact, in many cases, the camera was recovered and the film was able to be developed. The photographer is no longer with us. Almost nobody could survive these. If you were far enough away, there were a few loggers that actually survived it, but 57 people died in this blast because they were too close to the mountain. 1902, the town of Saint Pierre in the Caribbean was blown away, was destroyed by Mount Montpellier, the mountain. The volcano here had a pyroclastic flow and turned this peaceful town in the Caribbean into this. Okay, this is what these things do. They incinerate everything in its way. Okay, now we're looking back at Mount St. Helens, and we're looking at the pumice plain here, and we can see that this pumice plain, after it was first in place, was very hot, and so it was contacting, this hot material was contacting groundwater and creating explosions. So we have several of these multicolored explosion craters that are now filled with water in this pumice plain. Okay, the ash. Let's talk about ash for a minute. The ash, most of the ash went eastward, and you can see the extent of the ash went all the way to the Midwest. In fact, you should have gotten sprinklings of it here in your state. But of course, the ash was worst in the closest and a little more diminished as we get farther away. But what is ash exactly, and why is it such a hazard? If you look at ash under a microscope, it's not ash at all from your fireplace. It's frozen, it's little shards of microscopic glass. Think of little fibers of fiberglass. And so this stuff is just sprayed out during an eruption. And when rock cools immediately, it forms a volcanic glass. So if you look at ash underneath the microscope, you see that it is quite treacherous to have this in your throat and your lungs, as some people discovered. Okay, this picture was taken in eastern Washington, about 100 miles away from the volcano, on the morning that it happened, and there was no sound close to the volcano. The sound went up and over, farther away, was heard quite far away, but close to the volcano, absolutely silent. And these people stopped on the side of the road to see this ominous cloud coming towards them. This is in eastern Washington. It blanketed the whole landscape of eastern Washington, which can still be seen. This is not snow. We don't get it that much snow here. This is all volcanic ash. Creates huge problems for homeowners because it will collapse your roof. So people got up there and were digging it off, and road crews had to clear roads. This is taken in Yakima, Washington, which got so much ash that it turned the middle of the day black as night when that ash cloud came over. And they simply don't know what to do with all this ash. They basically took big piles of it and piled it outside of town. In a few towns, they built houses and shopping centers on it, which is a little bit shaky, but they did. It's a huge problem. And then, of course, the hazard that reaches the farthest away from the volcano is a lahar and a volcanic mud flow. So lahars form when volcanic ash and debris mix with water, and the water comes from melting the glaciers that are on top of the volcano. This all happens at once, and then it makes a mud flow. Well, they call it a mud flow, but it's ash mixed with water and flowing down. This is the lahar being initiated, the big lahar coming down the North Fork of the Toutle River. And this is what it looked like. It took out bridges, took out the road completely, took houses, huge houses like this off their foundation, moved them down the channel. And you can see the height of it here as it's coating these trees. It kind of, the water level came up and then it went down, and it totally took over the river valley. So when we look at this, this is on the south side of Mount St. Helens. So the lahars were coming off of all directions. The blast basically went north, but the lahars kind of went off the rivers in all directions. And this is one on the Muddy River, southeast of the mountain. But anything that is big enough, any flow that is big enough to move a rock that size has got to be horribly powerful. In fact, it totally buried the town of Armero in 1985 in Colombia. They had a volcanic eruption, just rather small one, of a volcano 30 miles away, came down this valley and filled and killed this town, killed a lot of 25,000 people in this small town. So these things are very dangerous, and they travel many miles away from the volcano. We map these now to see where they went in the past, because we want to predict where they will go in the future. And this is what the lahar deposits look like. They're basically ash with a lot of rocks embedded in it. And these can be traced all over the Cascades. Now we've basically figured out where a lot of the ancient lahars have gone. Okay, I also, I gave helicopter tours of this mountain for several years before COVID hit. And we would fly down the North Fork of the Toutle River. So I always gave a lecture beforehand so people would know what to look for from the helicopter. This is what the channel of the river looked like before 1980, just a typical Northwest stream. You can see the forest all around, and you can see landslide rocks in there, people fishing and so forth. But after 1980, this is what it looked like. And this is what it looks like today. Unmistakable evidence of, you've got ash everywhere, the stream kind of flowing through the middle of it. And, but it's just unmistakable. You take a look at this and you know that this was the site of lahars. Okay, so I think I've gone over all the disasters and all the events leading up to the eruption. Let's kind of look at what happened since 1980, okay, since that big eruption. Well, the whole north slope of the mountain is gone, and now it exists as this kind of huge ramp-like structure. There is a well-developed crater in the center, and there's a lava dome growing. It is still It's still pushing up magma. This lava dome keeps growing. Right now, you could fit all of downtown Portland in here. This is the size of this thing. It's just enormous. It's got a horseshoe type glacier all the way around it, and we watch it. We watch it carefully because we want to know what this thing could do in the future. Okay, so since the 1980 eruption, it's rebuilding itself. This is what volcanoes do. They erupt. Sometimes they erupt they build themselves up by repeated eruptions. Sometimes you have a catastrophic eruption, but as long as that magma is still there and still under there feeding it, then you have repeated eruptions. And so lava domes are growing daily in the crater. In the years following 1980, they mapped these all out, and I've got a picture of that I'm going to show you. But this is what it looked like. Small, steady eruptions just filling this dome. This is inside the crater. And you can see that it's still steaming a little. And here's another picture taken in 2004. So after, and it's still giving off lava. It's still erupting basically, but in a small way that is contained within the crater. Now, if we look at this, that they've mapped it all. So here's the crater of Mount St. Helens. You're looking to the north here, and that is Mount Rainier in the very distance. But you can see that the whole area, there's no forest left here. This was all decimated, but we're right inside in the top of the crater here. looking northward and down into the crater. They've mapped each one of these and which one each different lobe of this lava dome and what year it erupted. So you can see it's continuously growing. So now what? What's going to happen now? Well, if it were to keep building at the same rate that it is going, in about 200 years, it'll be back to its original size before the 1980 eruption. So will another eruption happen? Well, right now, I would say it's erupting, but it's very small. It's contained within the crater, so we'll call it the dome building stage. But another big eruption, so that means that another big eruption, a catastrophic one like in 1980, in the near future is unlikely. This causes a lot of problems, though, and especially in the years after 1980, anytime anybody said, well, Mount St. Helens is erupting, everybody's, getting all worked up about it because they don't know how big an eruption that they're expecting. Eventually, though, given the past history of it, and you saw what it's done for the last 4,000 years, you're going to have another large-scale eruption eventually. Okay, so we can't predict exactly when that's going to happen. So our best defense is continual monitoring. And that is how we developed the US Geologic Survey, developed the Cascade Volcano Observatory, which was established, kind of hastily put together in the months before the 1980 eruption, and is there now to monitor all of our volcanoes because, we can still see active steam in there. We know the volcano's hot. And all our neighboring peaks here. We live in the shadow of Mount Hood. I live farther south in the Willamette Valley, and I live in the shadow of Mount Jefferson. So all of these are active volcanoes. Mount Rainier up in Washington is the one that's deemed to be the most dangerous by the USGS because of all the people that live downstream from it and all of the rock that is decomposing in the center of it. Could have a lahar even without an eruption. Mount Hood, it forms the backdrop of Portland and is still an active volcano. And then Mount Jefferson, where I live, I don't have a picture of it, but Three Sisters further to the south. These are all active volcanoes. Look at this nice fresh lava flow that you can see in the foreground here. These are being studied. And of course, the Portland area itself is built in a volcanic crater. So it's built in a drop-down basin, but it's a volcanic field. So all of these little bumps, you can see Mount Hood here in the background, and this is downtown Portland. And all these bumps here on the other side of the river, these are all volcanoes. Now they are not stratocone volcanoes; they're monogenetic cinder cones, meaning that they erupt once and they're not expected to erupt again. But this is a very, very interesting place that's dynamic landscape that is always changing. Okay, I just want to end up with a few kind of thoughts on what volcanoes done and what volcanoes have done throughout human history. So if we want to go back in time, we want to go to the eruption of Thera, which is now called Mount Santorini in the Aegean Sea. And it was the start of the Greek language and culture. This large eruption happened during the Bronze Age, which completely decimated the Minoan culture that was living there. And the Greeks came in and took over afterwards. And so you can consider, and of course, Greek language and culture is part of Western civilization. You could say it started there with a huge volcanic eruption. Mount Tambora, more recently in the year 1815, erupted, and it put so much ash into the atmosphere that it changed the weather. We had, the next year was called the year without a summer. Massive starvation was going on. It was snowed in July in New England, for example, and ruined the crop, completely ruin the crop and so forth. And this actually started the Frankenstein story. So Mary Shelley and her colleagues were sitting around in a gloomy England summer. It was like it is in Oregon. It rains all winter long. And then we have a beautiful, in the spring, it starts clearing up, and we have a few months in the summer that are nice and sunny. And we look forward to those. Well, England has a very similar climate to ours, but the rain never stopped. It went all through the summer and all through the next winter. So they were getting rather morbid by the end of this, and they were telling ghost stories to kind of cheer themselves up. And that's how Frankenstein was born. Mount St. Helens, though, was an important contributor to modern volcanology. In fact, you could say modern volcanology started in the United States with this eruption of Mount St. Helens. We created the Cascade Volcanic Observatory, the CVO, it's called, and it resides now in Vancouver, Washington. And then we also had a volcanic crisis assistance team that was started by Norm Banks of the USGS, and that was in response to this eruption. Now it later changed, got different funding and became the VDAP program, Volcanic Disaster Assistance Program. This is a team of volcanologists that anywhere around the world, when there is a volcano threatening in any country and they don't have local volcanologists that can handle and mitigate the crisis, they go there. They pack up their bags and they go there and they help with disaster relief and so forth. So very important and, very important contribution. So Mount St. Helens brought many new advances to volcanology, which we do apply around the world now to keep people safe from volcanic hazards. So I want to thank you very much for your attention, and I will take any questions. And I've got my contact information there if you are interested. Actually, this is old. Okay. Oh, I better update it with my new. You can always reach me at this bottom one. This is my PSU email. This top one, I'm sorry to say, my email changed a couple of years ago and I never changed this slide. So forgive me. My new email is Sheila Alfsen at viclink.com, at gmail.com. I'm sorry. The Viclink is no longer supporting email. So sorry about that. Anyway, I'll take any questions now.
Okay, this is Dave talking. I'm going to start with a couple of questions of my own. If anybody has questions, type them in the Q&A. I see that there's at least one there already, and we'll get to that in a minute. But my first question is, when you showed that ash map, it looked like there was a little disconnected area down in maybe Oklahoma.
Yeah.
I assume it went through the upper atmosphere and came down there.
Yeah, that's what I would assume too. And I don't know about that. People have always asked about that little teardrop shape that, that happened to land. It was probably atmospheric conditions that, brought the ash down in that area.
Okay, and then my other question is, you showed this map of the crater after the eruption and how detailed it is as to where they're, do volcanologists actually go down into the crater and sample in person, or is it done some other way?
Well, back in the older days of volcanology, yes, you see these people hovering over a steam vent and putting, now we have, actually my last visit to the CVO, because it's right here in Vancouver, and they have an open house occasionally, usually on a yearly basis. The newest thing that's happening is robotics. I mean, why send a person down in the crater? So now they have robots that are in there that are actually collecting steam samples and collecting things. It's pretty dangerous to be down in there, and they try to minimize, actual time for humans to be down in there.
So the robots dropped in by drones?
There are, I'm not sure how they get them up in there. That's a good question. Helicopters, there's a lot of helicopters in and out. So I think that they're dropped off by helicopters. And then, but I know that they're doing a lot of design for that, for the remote sensing. They're trying to get to a lot more remote sensing because of that, because you never know. See, there were foolhardy people in the 90s that went up into craters without, realizing. They didn't know that there were, now with long period seismicity, we can tell when it's getting very close to erupting. And there was one in Galeras, 1995, that was erupting, showing long period seismicity, but they didn't know how to interpret it, and they didn't interpret it as such. And these people went down into the crater, and several of them were killed and seriously injured, so that kind of thing you want to be very careful of.
Okay. One other, I believe, is it true that Dave Johnston basically saw the eruption and knew he was a goner before it actually took him?
I think so. From the readings I've done afterwards of people interviewing survivors, and like I said, I even gave this talk for a couple of the survivors that were with him the night before. Yes, he was not supposed to be manning the station. He took it over for a grad student who was managing the station and had to go away. And they knew that it was close, but they didn't know exactly how close. And he kind of was asked to replace him for the one night. And that was the critical night. But in interviews from people, 2 women geologists, volcanologists that were with him at the time, and they were hoping to camp nearby the observation tower, he started showing them the landscape, and he said, it is not safe here. This stuff can actually, the surge deposits go over hills and into valleys. They can go up over hills. And he said, it's going to reach this far. So I think, yes, he actually knew what danger he was in, but willing to do it because that was his job, and volcanoes were a passion, was a passion for him, just like it is for so many of us.
Okay, thanks. I have a
Yeah, I
series
think
of,
now they would have never put Coldwater 2 observation tower where it had they known it was going to shoot out the side. That was the wild card that they didn't know. See, and it was positioned perfectly on the north side of the volcano to watch the bulge, but they expected the eruption to go straight up. When it shot out the side, it turned out that, it turned out to be deadly, unfortunately.
okay, I have a series of related questions from you. Is the forewarning seismic activity attributed totally to magma movement? And is movement of the Juan de Fuca plate partly to blame? And if so, can its movement be detected?
Okay, yes, the Juan de Fuca plate is the culprit, but not because it's moving, and it's not moving and creating those earthquakes. The earthquakes are moved by magma coming up through the surface. Remember, to have an eruption, it has to find its way to the surface. And so it kind of moves the rocks and cracks them a little, and then it finds a way to get to the surface. It's like gas, it's got a lot of gas. It's under enormous pressure, and so as that magma is moving up, it's creating these small earthquakes. So they were having earthquakes in several months before the eruption, and people that lived close by said that they felt the rattling all the time, like while they were in bed, they felt the rattling, and any time during the day they felt the rattling. But on the morning of May 18th, this was a much larger than usual earthquake, and it shook enough to shake that oversteepened bulge, which caused it to fail, which took the cork off the bottle. So as far as building up pressure with the Juan de Fuca plate, that's a whole nother subject about the subduction earthquake. Yes, it has the potential to create a huge, enormous earthquake. And I'm talking 10,000 times bigger than the one that initiated the eruption of Mount St. Helens. And, you know, this is how that works. And that's a whole subject for another time. And I can definitely give a talk on that. Yes, it is building up pressure, but that was not the earthquakes were the result of local activity with the magma chamber itself and not with the whole plate.
Okay, thank you.
Yeah.
A comment from Doug, just great presentation. Thanks so much. And then a question from Bob. Is there boating, etc., active in Spirit Lake now?
Is there what
Boating.
No, it's not that I saw. And I've been doing there's a lot of helicopter tours. So a couple years ago, I gave a helicopter tour for the Geologic Society as a field trip. And then the folks that were there running the helicopter, they liked it so much that they asked me to open it up and do it for the general public, which I was going to do. And we were all set up for the 1980 or for the 40th anniversary in 2020. And then COVID has kind of changed that. So I don't see any activity in there. The whole thing is, but what's interesting is there's some interesting things going on. The whole thing is got diluted silica in it from the ash. So the silica kind of leaches out and is in the water, and those logs are turning into petrified wood right before our eyes. Or it's happening, it's being studied, and it's happening much faster than we think. So no boating or recreation that I could see and that I know of, but there's all these logs floating around. There's quite a bit of research being done on them. And we're getting kind of more of a handle of how petrified wood is developed, forms.
Okay. Here's a fairly long question from Peter. When a nuclear weapon surface blast occurs, the radioactive dirt from the mushroom cloud that falls back and spreads out laterally is called the base surge.
Yes.
Is the pyroclastic flow the same sort of thing for volcanoes? Why doesn't the pyroclastic flow cool down? And is the heat or the toxic gases or the glassy ash that make it dangerous?
Okay. The pyroclastic flow is powered by gas underneath there. That gas is under enormous pressure, and when it releases, it shoots up into the air. But how a so you've got ash and you've got gas. When it's too dense to go up, it actually rolls down the side of the mountain. And it's being driven and powered by gas. So it's more than just rolling down the side of the mountain. It's being shot out down the mountain. And, so that's why it's moving so fast. So pyroclastic flow is basically when a vertical eruption collapses on itself because it's too dense. And then it goes down the side of the mountain. Then if it's in between that, and it's got more gas than ash, then we call that a surge. And that has the ability to flow down, not only flow down into a valley, but go up over hills. In fact, it was the surge that got volcanologists in the eruption in Japan in 1991. That, in fact, some of the volcanologists were ones that were working on Mount St. Helens. And then they went to Japan in 1991 to watch this. And it was a surge that came up over the hill and killed them all too. So volcanology was a very dangerous science. That's why we're doing a much more remote stuff. I probably got off the subject a little. Do you want to reiterate the rest of the question for me?
Sure. I think you said earlier that the flow might go as fast as 600 miles an hour. So basically the speed of sound. Is that correct?
Yeah, yeah. Or
So,
faster. That's why, you know, it was silent right around the volcano. There were loggers working in the forest that day, that Sunday morning. There were still logging operations going on, even though it was zoned off and you weren't supposed to be in there. Weyerhaeuser was, you know, kind of pushing to get some of the logging done because nobody knew exactly when it was going to happen. And they didn't hear a thing when that flow came crashing through the mountain. They heard trees snapping and they heard, you know, the effects of it, but they never heard any effects of they never heard the sound of the actual eruption. So the sound went up and then over, and it was heard for hundreds of miles away, but not close to the volcano, completely silent.
and then other parts of that question were, why doesn't the pyroclastic flow cool down?
It does, but it's still pretty hot upon emplacement. So, and there's so much, it does towards the very distal edges, like maybe 15 miles away, it cools down enough to sear the trees, but not blow them down. And that's why you've got the seared zone. But, you know, so it does cool down, but, you know, so much of it wasn't placed in the pumice plain, like 150 feet. The Toutle River, the base of the Toutle River is 150 feet higher than it used to be. So you dump that much hot ash there that they were roasting pigs. The USGS had a party about a month later, you know, because they had been working nonstop, and they finally, you know, and they decided to roast a pig in the ashes about a month later. It was still hot enough to roast a pig. So yes, it does cool out at the outer fringes, and that's why you have the blast zone, the channelized zone, and then the sear zone around the very edge. And then it runs out of heat, so there you have untouched forest beyond that.
And then the last part of his question was, is the heat or the toxic gases or the glassy ash that make it dangerous?
Oh, all three. Survivors said, and they have found animals and people, unfortunately, they breathed in so much ash that it actually seared their throat, but it also sealed it. And in some cases, in other places, I'm not sure exactly with Mount St. Helens, but in other places they found what's, you know, remains of people, and they had to just chip the ash out of their throat. It just, you know, you get swamped with this. Even breathing a little bit of it is dangerous because it's like little shards of glass, you know, but breathing so much of this hot stuff to where it actually closes your throat, you know, and forms a plug in there is, you know, serious. Now, what's amazing is, well, they can record the heat and the heat basically by taking, there were leftover objects. There were people that were photographing it in their camera. You know, there were actually one body that was hugging its camera to try to protect its camera, you know, and some of those, some of that film was actually developed. That was in the days before digital cameras, and we had film, and some of the film was actually able to be developed. But what they do is they take a similar camera and they cook it in an oven to see how much melting occurs, and they match that to the stuff they found out there so they can get an idea of the actual temperature of it by the artifacts that were left behind.
Okay, here's a question, another fairly long one from Alan. I and my family visited the Mount St. Helens area in about 2012. We only got up as far as what was a lake. Based on the information available at that time, you can hike up in the volcanic area for one day. You can only stay in the vicinity for perhaps 8 hours. Do you have additional information on this?
No, I don't. I know that there's several trails hiking up to the crater, and they are on the south side. The south side was basically untouched because most of the eruption went to the north. So there's several trails on the south side. And I don't know what the current situation is. And with COVID, I really don't know. But I know that there are trails and it can be hiked. It was hiked by some of my students once, which was amazing, so it can be hiked. It's a little more expensive, but it's particularly rewarding to fly over it in a helicopter. And, again, to see all that. But I don't know much about the restrictions. I know that it's being watched very carefully, and we have a much better handle on volcanic eruptions. Now, earthquakes, those are the hard ones. We can't predict those ahead of time, but I don't think a volcanic eruption is going to take us by surprise. I think we've developed enough understanding of all these precursors to be able to kind of pinpoint it pretty well. Hopefully. Of course, they all behave differently. So there's that consideration as well.
I know in 2003, my two youngest brothers actually hiked up on the south side, as you said. And they said when you get to the top, there's a lot of signs there warning you not to go close to the edge. And they said nobody in their right mind would go close to the edge because it is obviously so unstable.
Yeah, it's very unstable and very steep, and you don't know how solid the ledge is. Yeah, I've been in Hawaii on some of those situation like that. You could see across the other side of the crater that was just a very thin rim, and you had to assume what you were standing on was a very thin rim, and you just have this desire to go look down on the bottom, but you can't get that close to the edge, because you don't know how unstable it is. So I think that's a consideration. Another thing is there's active steam going on. And when I did my field camp there back in 2004, I think it was, there was somebody that brought a rock that had just cooled that was part of a lava flow. And they were going in there with helicopters and sampling things and bringing it out. So we were at the visitor center or somewhere down around the developed area around the mountain. And this guy brought a rock, and I think everybody in our group just went, "Oh my God, a baby rock." We have to go see what this, whatever the mineral crystals look like. And, we were all had our hand lenses and looking at it. So it's still producing. Oh, wait, I'm sorry. Let me turn off. Sorry about the phone. Yeah, it was still, it's still active. It's still doing its thing.
Okay, a question from Mary Helen. Is the magma underground and the lava erupted out of Mount St. Helens, is it more silicic in nature or more basaltic?
Okay, I'm sorry. Repeat the question. I was kind of
Is the magma underground and the lava erupted from Mount St. Helens, is it more silicic in nature or more basaltic?
Okay, it's right in between. It's intermediate. Okay, so mafic, and this is one of the big misconceptions that people had that didn't, like myself, that didn't know much about volcanoes. I was not a volcanologist in 1980. I wasn't a geologist at all then. I always thought eruptions were like Hawaii, where the lava just flows, and there's streams of lava, and wasn't expecting this big, messy, cloudy, gray, ugly, dangerous eruption. So mafic lava does erupt like Hawaii, because it's less viscous, it doesn't trap as much gas, and it's not as explosive. Felsic is very explosive. And all the rocks that make up all the cascades is andesite, which is intermediate, about halfway between the two extremes. But enough to be explosive. In fact, the rock that it's made out of is called andesite, and we named that after the Andes in South America. Same situation, same kind of rock.
Okay. Right now, there's one more question, which I'll read, but if anybody else has another question, now's the time to enter it. The GSM visited a site in southeast Nebraska, which was covered with volcanic ash 14 million years ago. They are recovering ancient mammals. The animals were inhaling the ash and going into water depressions to cool off, and they ended up dying. I believe it's close to the Niobrara River. And I was on that field trip, and I don't remember the name of that site, but it is it was a very interesting site because it's all, it's covered. They have a roof over it now, and so you can see all these animals in situ. It's pretty nice that way.
Yes.
If anybody recalls the name of that, you can type it in.
Yeah, I was actually at Ashfall State Park, and that was one of the Yellowstone eruptions, the ash was.
And see, when you're talking Yellowstone, then you're in the realm of being felsic. So like intermediate, mafic flows the running lava, intermediate builds stratocones, but the huge eruptions that dump lots of ash like that are felsic in nature. And we have the same situation in Oregon. So we have the high lava plains, which was one huge felsic eruption after another, and it preserves. It's a wonderful preservation for fossils. Nothing like entombing all these animals in hundreds of feet of ash, and scavengers can't get to the carcasses, so it preserves fossils very well. We owe a lot of our fossil record to volcanoes, believe it or not.
Sheila, this is Steve Erickson again. How are you guys doing tonight? That's an excellent talk.
Oh, thank you.
When I was going to Long Beach State back in the early 80s, shortly after Mount St. Helens, I was a freshman level geology student when that took place. But then there were some rumblings up in the Long Valley caldera.
Wait, I'm sorry.
Uproar there. People were upset because they were predicting an earthquake or the volcano erupting there, and didn't happen. But I know that the USGS still monitors that. What's the latest that you know of going on in Long Valley?
Oh, Long Valley caldera. Oh my gosh. In California. That's that one is a nightmare, because what is the name of the town that goes that's close?
Is that Bishop that you're talking about?
Bishop, I think it's Bishop. Or there's another one where there's kind of the road out of there, evacuating would be a complete nightmare.
Mammoth Lake.
Is it Mammoth Lake? Yeah, I'm kind of forgetting my California geology or my California geography. But yeah, they're worried about Long Valley caldera, and it's a kind of a horse of a different color. It's a different beast. It's basically, it's not a stratocone. It's basically, I think it's the old Farallon plate still under there causing, remember the Juan de Fuca plate, the one that's causing all in the Pacific Northwest, used to be a larger plate called the Farallon plate that subducted under California. So the Sierra Nevadas were volcanoes, stratocone volcanoes, and subduction was going on. Then when the San Andreas Fault initiated, it was because the continent overrode most of the Farallon plate and left just the little remnant that was sticking out to the west, and that's the Juan de Fuca plate. And the San Andreas Fault is under but that plate is still under there, festering. So I have good friends that are California geologists, and that's what they think is going on, that it's still festering under there. And I think they are worried about it because evacuation would be very difficult. And when I say that we've gotten good at predicting volcanoes, I'm talking stratocone volcanoes. because that's what we've studied a lot. And those are the ones that give us enough warning that we're getting pretty good at predicting them. But other volcanoes and Yellowstone, which is the hot spot, which is under there festering, when it goes, it's going to be off the chart, And I don't know that we could predict an eruption of that within any given time frame. Oh, I hope that answered your question.
Yeah, that was very good. I know that you could talk, that's a whole hour-long conversation on that one, but like I said, I remember hearing about it, and there was a number that was given to us at one point. Somebody passed some word to somebody that passed some word, and we picked it up as geology students there. They were talking about 2 or 3 meters of ash in Denver was one number that was bounced around. I have no idea where that number came from or who started it, but that was a guesstimate that they were talking. And when you look at these big volcanoes that have erupted through Long Valley and such, it can do that sort of thing, but exactly how much and how many and such is always, I never found out where that source number came from on that, though.
Yeah. I don't know about that particular thing, but I can tell you that, well, you saw that chart that I showed of Mount St. Helens, which, when you saw the Rosenquist pictures, that looked pretty big with the eruption. And it was just a pipsqueak compared to Yellowstone, and that's just like almost hard to imagine. It's unbelievable. And the ash from that would be, the ash from that is found all over the place, So, yeah, geology can be a very sobering subject if you think about what could happen, but,
Yeah. Well, anybody has other questions, that'd be great. Otherwise, maybe we can finish her up for tonight. Thanks, Sheila. Appreciate it very much for your talk.
I am
Anybody
glad.
else?
I didn't see any more questions in the Q&A.
No more questions? You didn't see any?
There's no more questions, right?
Okay,
So we had close to 75 people listening tonight, so a nice crowd.
good.
And thank you. Like I said, I visited there in 2003, so it was very interesting to hear all about it again.
Yeah,
In 2 weeks, we are going to hear about the geological provinces of Georgia. So go in the opposite direction from Minnesota.
yeah. Well, geology is fun no matter where it is. It's also different. So, and yeah, good. Well, thank you for having me, and it was a pleasure. Yeah, so we look forward to you folks joining us at GSOC too. We have a lot of geology to share there too.
I missed the last one, but I'm going to try to catch the next one. Thank you. Have yourself a good night.
Thank you very
Okay.
much.
Okay, I'll stop sharing here.
All right.
Okay, and I'm just seeing a lot of black squares, so
Yep.
people don't have their camera on. Let me see, I
came in.
okay.
Yeah.
I moved over the questions and it looks like we covered all of them, huh?
Yeah, yes, we have.
Yeah. Okay, good.
Well, Sheila, when you said you don't want to stand on both sides of the crater, I actually did that when I climbed Mount St. Helens back. It was when I was teaching out in that area, but I got a picture of it, but I wouldn't want to do it again.
That's so interesting. It's a pretty strenuous hike up to the top, I imagine.
It is.
There's several different trails on the south side. And then you have, I definitely enjoyed the helicopter trip because I was able to talk to the pilot and tell him where to go. And I want, so we kind of planned out a good route that went over all the disaster zone and then circled around. Then we actually get into the crater fly around inside the crater and then down the Toutle River. And that was, so you could get a really good view there.
Yeah. All
Yeah.
right. Well, again, we thank you very much, and it was an excellent talk.
Okay, well, I'm glad you enjoyed it, and I guess you recorded it, so it's there. Okay. And
Yeah,
I'll,
we'll send you the link to the recording in a few days in case you're interested.
okay, thank you. Yeah. Let's see. And also let's see, Bill Orr and I gave a talk on assembling Oregon a few months ago. Do you can you send me the link to that too? There's some classes that I may want to use that for.
Yes, I can send you the link to that also. We still have that, right?
Okay, yeah, thank you.
Eventually, we're putting it on YouTube, but I don't think it's there yet, but we have a place it'll last for close to a year, I think. And then after that, it'll be on YouTube for
Would
longer.
students be able to, if anybody with the link would be able to watch this, right?
I'm pretty sure, right, Randy?
Yeah, that's correct. Yeah.
Okay, because that would be, I think with remote teaching and trying to do kind of a hybrid in-person and remote, it's nice to have some backup like that. And next term, I'm going to be doing an overview of Oregon. So that would be very handy.
Sure.
So thank you. Okay, well, I'll go and see what the telephone wants. I got several calls.
Okay.
Thankfully, it didn't ring during the lecture. So, okay.
Again,
Okay,
thank you.
thank you once again. Goodbye.
Good night.
Bye.